forward to the next talk. It's by Hanieh Fattahi. Hanieh studied biophysics at Sharif University in Tehran, where she received her Master's of Science degree in 2007. Afterwards, she joined the Laboratory for Advanced Physics, headed by Professor Ferenc Krauss in Munich, and she was awarded the PhD degree in 2015. More recently, she's become a research group leader at the Max Planck Institute for the Science of Light in Erlangen. So, Hanieh, the floor is yours.
Thank you very much, Bob. So let me try to do this very scary moment of sharing my screen. So do you see my screen?
Just we see. Just press swap at the top because we see the speakers now. Top left. It says swap displays at the top left.
So I don't have any top. Is it
right there
now? Ah, okay. So what should I do exactly?
No. You have to click. Press swap displays on the top left.
Oh yeah, I saw it.
Yes, perfect.
Oh, but then you see now you see the presentation mode, or
just the presentation, not the notes.
Okay, perfect. That's good. So thank you very much, Bob, for the introduction. Hello, everyone. I would like to thank Paul Corcombe and Bob Boyd for inviting me and organizing this excellent symposium. I've been active in the field of attosecond and femtosecond science for about a decade at Max Planck Institute for Quantum Optics. As Bob explained, I did my PhD in the chair of Ferenc Krauss in the attosecond division, and later on I started to lead my research group there. During this time at MPQ, so let me just activate my laser pointer also. Okay. During this time, my focus has been on advancing the required technology for attosecond and femtosecond physics based on ytterbium-YAG thin disk amplifiers. They are a desired technology these days because of their scalability in average power and energy. So we demonstrated that by combining this technology and optical parametric check pulse amplifiers, multi-joule few cycle pulses can be generated. Therefore, we dubbed this technology together, the ytterbium-YAG thin disk lasers and OPCPA as third generation femtosecond technology. If you would like to know about it, I just added some of our references for your information. Later on, we demonstrated that based on this technology, one can generate very exotic non-sinusoidal pulses by using coherently combining of several few cycle pulses. And then I just listed some literature of our group that if you would like to know more about this. And then we went even further and showed that one can reach exotic wavelengths from ytterbium-YAG thin disk lasers and reach very high power mid-infrared and terahertz pulses. And me and the group worked on petahertz field sampling and some novel techniques to detect the electric field of light at petahertz frequencies. So then in 2020, in the beginning of the pandemic, I moved to Erlangen and started to lead my research group at Max Planck Institute for the Science of Light. And then here, based on my previous expertise on novel ultrashort pulses and novel detection metrology, then I started the group with two major focus or two pillars. So the first one was to realize the application of this kind of technologies in spectral microscopy, which we call or we dubbed femtosecond molecular fieldoscopy. And I'm gonna focus on this quite a lot today. And then the second pillar is to generate bright mid-infrared pulses for gas spectroscopy. I'm also going to talk about this direction at the end of my talk a little bit. So, but beside these two main focus, we also have some other small projects. For example, we are developing some new detection techniques. My student has a poster on Friday, Mohammad Sadiq Bafai-Nejad. So I encourage you to visit him. We are using the technique of time lens to detect the short pulses in a very fast manner. We recently started to look at high harmonic generations from silicon carbide, and some terahertz spectroscopy of sugar is taking off. A project on sugar is taking off, and we also have some fun projects. Like we started recently to build a sun pump laser. So if you are interested to know about these other projects, just please feel free to contact me. We can have a Zoom meeting and have a chat about it. So let's start with the main pillar of the research in my group, which we dub molecular fieldoscopy, and see what it is and why we invented this new name somehow for this. To set the stage, let's think about light. So light is one of the most important tools for a human being to understand its surrounding, from giant galaxies down to small molecules. As it is very well known for optics community, Abby in 19th century discovered that the spatial resolution in any optical imaging tool, such as a microscope or telescope, is defined by the diffraction limit of light, which is proportional to the wavelength of the light. And then this means that if you would like to look at smaller objects with light, then you need to use the light at higher frequency. And then based on that, he defined the Abbe's diffraction limit at 0.2 micrometer or 200 nanometer, which is half of the highest frequency radiation visible to human beings' eye. So this barrier has been overcome by super resolution microscopy. In conventional microscopy that you can see, I'm just referring to biological microscopy in this talk. One just has a sample that would like to image, and to do this imaging, one would need to label the molecules in the sample with some fluorescent molecules. And then you need to tune the excitation laser to the excitation frequency of the labels, and you gather the light which is emitted from these labels. And that's, of course, limited to the diffraction limit of light. So in super resolution microscopy, which is pioneered by Stefan Hell and Eric Betzig, the spatial structure of light or transition of these dye molecules or labels, or even the time dimension, is used to make sub-diffraction limit images. And they could go even down to 80 nanometer, which is very impressive. So these beautiful works, I don't need to advertise for them because they were already praised by the community with a Nobel Prize in 2014, and they are opening new routes in biology. However, at the end of the day, you need to label your samples with some fluorescent molecules to be able to do high resolution, super resolution microscopy. So these labels, most of the time, they are very big, and they perturb the function of the molecule that you would like to observe. And besides that, there is no chemical information about the sample that you are looking at is gained in this type of imaging. So then the question is that, is there any way to avoid labeling and get also chemical information? And the answer is that, of course, one can just look at the light, which is directly emitted from the molecules themselves, or they are absorbed by the molecules in the sample themselves. It is very well understood that the fundamental vibrations of the molecules are in mid-infrared to far infrared spectral range. This region is known as a fingerprint region, as here molecules show specific absorption or emission lines, and one can track them back. One can gain similar information in near infrared spectral range by observing the overtone excitation or Raman resonances of the molecules in the sample. So This kind of microscopy that one look at the signal from the molecules themselves, it's called label-free spectral microscopy. And then what the only thing that you need to do, you need to tune the excitation frequency of the laser to the resonance of the molecules in the sample. But we just saw in the previous slide that the resonance frequency of the molecules, they are at mid-infrared and near-infrared spectral range. And then we know that if you move to longer wavelengths, then you lose a spatial resolution. That's why the label-free spectral microscopy is not it doesn't have high spatial resolution. So the situation is even more complicated, because if you would like to look at soft matter and biological samples, the phototoxicity increases when you move to shorter wavelengths to get the higher spatial resolution. So then the question would be that what is the best wavelengths to start with, and how we can just have a label-free microscope, spectral microscope with higher spatial resolution. This is the challenge that we picked in our group, and we are trying very hard to realize it. So just to I just go back to the first question that I raised, that what would be the best wavelengths to start with. This is a study that we did in a collaboration with a group of Daniel Werner at MPL. So we performed an in vivo study on zebrafish at 3 different wavelengths. So we irradiated zebrafish with femtosecond pulses at 343, 515 nanometer and 1030 nanometer. And then we observed the damage in the fish and the threshold of the damage for these 3 wavelengths. So of course we chose the zebrafish because it's transparent and one can see inside how the damage develops. The result was very interesting for us because we saw the linear scaling of power and the damage for 300 irradiation with 343 nanometer and 515 nanometer. But for the 1030 nanometer irradiation, we saw a very nonlinear behavior. So we could see that there is a cut on the damage of the for the damage of the fish. And the other interesting point on this measurement was that the penetration depth of light at 1030 nanometer to inside the fish was quite interesting. So here you can see the fish, which is genetically labeled by fluorescent labels. So the neural system of the fish is now shown in red. And then you can see that the damage spot after this threshold that we could put on the fish. And you can see that we even reached, by increasing the power, we could even go very deep and cut the neuron, the spinal cord of the fish. So this shows that how the light at 1030 penetrates very well in the deep tissue, penetrates deep in the tissue, and also allowed us to damage the spinal cord at a very high irradiation power, which is 600 milliwatts, very impressive, I would say, while the fish stayed alive. Then I would, based on this study and all these arguments that they are sitting here, I just would like to draw your attention to this spectral range, which seems to be a very interesting one for building a microscope around it. If I go back to the molecular vibrations that I showed you, then the very interesting region is the near-infrared spectral region, as it offers us a higher spatial resolution compared to the mid-infrared one and higher penetration depth compared to the mid-infrared for label-free spectral microscopy. But if we go to the Abbey's rule, then we see that if we do spectral microscopy at this region, at the best case, we are gonna have a spatial resolution of 500 nanometer. And this is not good enough, right? So therefore, we developed a detection methodology to break this barrier in the spatial resolution. And to explain the technique easier, so let me start with conventional method. So spectral microscopy is in principle spectroscopy with a raster scan, right? At each point, I just gather spectroscopic information of my sample, and then I move the laser point by point to make an image out of it. The very common method to gather this information, of course, is frequency domain spectroscopy. Imagine that you have a sample containing so many different molecules at different resonances, and then you irradiate this sample with a broadband light containing frequencies that matches to the resonances of the molecules. Now, if you look at the transmission light, you see some absorption lines, of course, in the spectrum which is transmitted. And the depth of these absorptions, they are linearly proportional to the concentration of the molecules. So this has been a very wonderful and successful technique. But if you have a low abundant molecule in your system and your laser is a bit noisy, then you will lose the chance to see it. If we look at the whole process now in the time domain, or let's see what is the picture in the time domain, then again, you have a sample containing of different molecules, and you use a broadband excitation pulse, or in the language of time domain people, a femtosecond pulse, to irradiate the sample. And when you look at the transmitted light, you see the formation of molecular response at the trailing edge of the excitation pulse, which is exponentially decaying. So if one can measure this electric field and Fourier transform it, then one would get exactly this spectrum. What is the catch here? Here, the catch is that the excitation pulse is separated from the molecular response. Then it gives us a chance for a higher detection sensitivity and dynamic range. And of course, by using a short pulse, one can cover the entire molecular vibrations at once. But then the problem is how to measure this fast oscillating electric field of light. This type of measurements has been done routinely at terahertz and mid-infrared spectral range, but they haven't been extended. This kind of measurements didn't extend to near infrared and visible because and at petahertz because just the electric field oscillates so fast. And that has been the business of attosecond streaking, to just catch this kind of field oscillations. But of course, if you want to do attosecond streaking, you have to put everything in vacuum. Then you have no chance to look at live systems or biological samples. In my group and in collaboration with Nick Harpovich, who was my colleague at MPQ, we developed a system, a metrology that one can measure this fast oscillating electric field at petahertz frequency in ambient air. And that opened the route for the project that we are doing at the moment in Erlangen. So how do we do it? Then like so many typical ultra-fast measurements, you have a pulse which you would like to sample. And for this, you need a probe pulse, which is shorter than half cycle of the sample pulse. And you would need to look at the correlation between these two pulses at different timestamps, at different temporal delay. So what is this correlation? Of course, in terahertz, one can use electro-optic effect or mid-infrared, but unfortunately, there is no electro-optic effect for near infrared and visible. And what we do instead, we just generate some frequency between the probe pulses and each time delay relative to the sample pulses. If I take you now to the frequency picture, so this is the spectrum of my sample pulse. The probe pulse sits here at higher frequency because it has to be shorter. Then as these two pulses are all very broadband, the sum frequency has a region at a lower frequency that has an overlap with my probe pulses. So this is the only region that we filter out and we look at it because one has interference, right? And it has phase information in it. And the polarization rotation of this overlap region, if one can measure it, then it is gonna be proportional to the electric field of the sample pulse. So this is what we do. We put a short pass filter to filter out this overlap region, and then we just do a standard ellipsometry measurements with balanced photodiode. And we resolve the polarization rotation, and then as it's linear to the electric field of the sample pulse, then we can get the electric field of the pulse. But there is one more advantage in this system, besides having broadband detection and so on that I mentioned. The catch is that the spatial resolution here is defined by the overlapped region. Why? Because I have a short pass filter, and the signal that I look at is only the overlapped region, which is here, at very higher frequency. Then it immediately means that I'm getting higher spatial resolution information when I do this kind of detection. So I think now you know how our microscope works with this explanation. So we would like to do label-free spectral microscopy, but we would love it to be high resolution. The nature forces us to sit at near infrared or mid infrared spectral range, and that doesn't have enough spatial resolution. So we play this trick that we do this kind of field detection where we push our probe pulses to the highest possible frequency, and we keep our excitation pulses at near infrared for also the reason that I mentioned with our zebrafish measurement, that it's more friendly to the tissues in terms of damage. And then if you just couple these two lights to your objective, and then put your sample in contact to the nonlinear medium that you have to generate this response, then you can do point-by-point measurements and get spectroscopic information and make an image. So this is the setup that we aim to build at NPL at the moment. But of course, we needed some proof of principle measurement to make sure that if we can really nicely detect this molecular response or not, or if our device is sensitive enough. So then during my time at NPQ, we performed this measurement in my group that we developed a system which was operating at 5 kilohertz repetition rate, and we could generate this broadband excitation pulses centered at 2 micron and the probe pulses at 1 micron. Then we just choose water as it absorbs at 1930 nanometer. This is the combination band. And we used acetic acid as a buffer in our system because it's just transparent in this range. And what we did, we just mixed a different concentration of water and acetic acid in our sample holder, and then we just shined the sample with our excitation pulse. And we looked and resolved the electric field of the transmitted field by our short probe pulses at 1 micron. So here I just show you some measurement that we performed. Here you can see the case of the empty cell. This is the pulse that we send to the system. And the blue curve shows you the case that the cell was filled with 100% acetic acid. And you can see that they are one-to-one overlay. At this inset, this is just a magnified portion of the trailing edge of the pulse, because that's where I'm looking for my signal. So now in the next measurements, we just fill the cell with different concentration of water. And if my PowerPoint, yeah. And then you can easily see the formation of the free induction decay or this molecular signal at a different concentration of water. So this was a proof of principle for us that the technique is sensitive enough to catch the response. But of course, the system was working at 5 kilohertz, and that was so slow, so noisy, and it was a giant system. Then I got this position, of course, in Erlangen, and I had to rebuild the system, and we thought about an upgrade and to extend the system to megahertz repetition rate. Why? Because if we have a megahertz laser as a front end, we can do fast scanning, and we also get higher signal to noise ratio due to this 1/f noise law, right? We can go to the shot noise and remove the noise in our measurement. But of course, going to megahertz repetition rate is a very challenging business. That's why everything is hindered at this high repetition rate and high power sources. Because of course, the very obvious one is the thermal issues that they exist in this repetition rate. And most of the systems at this, the current laser system, they also have low peak power. And that limits the spectral broadening. Techniques that one can use. Sorry, I had a cold. So, at NPL, we started a collaboration with the group of Philip Russell and Francesco Tani. And we opted for a double stage fiber compression. So we started with a carbide laser, commercial one. I'm very sorry. So I lost my voice yesterday, so I'm very happy that I have it today, at least a little bit. So the pump operates at 1 megahertz, and after one fiber compression, we could compress our pulses to 26 femtoseconds. The second fiber that we implemented in the system works based on soliton compression, and we could achieve such a broadband spectrum and 6 femtosecond pulses. So these pulses are ready. Then we just splitted 20% of them to probe our electrode for our field detection, and the rest is sent to a BBO crystal for intra-pulse DFG. And to generate the excitation pulses, and we did also that, and you can see the very broadband spectrum that we generate. So where are we at the moment? We have the excitation pulses and probe pulses ready on the system. And in parallel, we also developed the microscope head that it had to be home built, that we need to just to be able to couple these short pulses to the system and to go for imaging. And we are just some small steps away from coupling these pulses to the microscope and do our first proof of principle experiment for the high resolution microscope. So then I would like to just encourage you to stay tuned. I'm pretty sure by towards end of the next year, we are going to have very exciting results in this area. The second pillar that I wanted to present here was the generation of mid-infrared pulses for gas spectroscopy. So our goal is to just generate the bright mid-infrared pulses at megahertz repetition rate. This is a very attractive topic at the moment in the community. And the approach that has been taken in ultrafast community is to develop very powerful ytterbium YAG lasers and then down convert them in frequency via intra-pulse difference frequency generation. Of course, the process is very inefficient, and the race at the moment is towards building a more and more powerful ytterbium YAG lasers to overcome this deficiency. We chose an orthogonal approach, and that was not to make a bigger laser, but to improve the conversion efficiency, to work on improving the conversion efficiency. And the approach that we chose, we decided to use ytterbium YAG, the ytterbium YAG pump oscillator that we have, to pump an optical parametric oscillator which operates at degeneracy. So this project is done in collaboration with Marandi at Caltech. And the team on this project is actually very strong, that they showed the first performance of the system within some months, that I'm able now to present the results, the very preliminary results that they achieved. So the pump is a home-built ytterbium YAG thin disk oscillator, which is built in collaboration with Oleg Pronin, and it delivers 25 watts, 350 femtosecond pulses at 15.5 megahertz. So here you can see the spectrum and the pulse duration, the frog measurement, and the beam profile of the pulses. So then these pulses are used to pump an OPO cavity which runs at the subharmonic of the pump and at degeneracy. Then one gets 2 micron pulses CP stable at 30 megahertz repetition rate. So I just show you the very preliminary results, just fresh from the lab, that show you how you can tune the spectrum from being at from a non-degenerate operation to a degenerate operation, which is of course the one that you would like to have to get the CP stable pulses. So with this, then I would like to summarize my talk. I talked to you about femtosecond molecular fieldoscopy. We use this term in analogy with microscopy and spectroscopy, and we use fieldoscopy because we measure the field, the electric field of light. So this is an emerging spectral microscopy method, and it offers high detection sensitivity, high dynamic range, and one can achieve precise spectral and phase information, broadband detection, and in principle, it's a petahertz oscilloscope operating in ambient air. And this can be realized, of course, by a novel femtosecond high repetition rate lasers, ideally, and a novel field detection technology that we are using that allows us to do these petahertz measurements. The other part of the results that I showed you was about the watt level CP stable pulses at mid-infrared, which can be realized by combining 2 powerful technologies. The first one is the ytterbium yaktin disk oscillators, which are really in front these days, and combining it with optical oscillators, optical parametric oscillators at degeneracy. So then I have to talk about the most important people. This is the group that I had at MPQ. They did the water measurement and they developed the system that led us to do this measurement. And of course, all the papers that I referenced in my first slide, they were all done in collaboration with this team. And this is the team at MPL. And I would like to thank you very much for your attention.
Unfortunately, only one person's hand claps come through. But Hanieh, thank you very much. There was a fascinating talk that you gave, and I'm sure there are many questions. And once again, I will ask Dr. Upham to handle the questions.
Thank you, Bob.
Thank you, Bob. And thank you, Professor Fattahi. The first question I have here is related to the use of Raman and infrared that you're using to detect a wide variety of materials. Both of these processes are affected by fluorescence. And often fluorescence can mask things like Raman. With the broad excitation, because you were showing ultra-short laser pulses, can you eliminate this impact?
So for the Raman, if you are using stimulated Raman, then the signal is much higher than the fluorescence which is coming from the sample. And then what we are aiming for the Raman, so as soon as we show the first proof of principle, of course, we start to do the Raman spectroscopy and microscopy. What we aim to dig the signal from the stimulated Raman process and not cars. So cars, of course, you have a background which is coming from the non-resonant response of the sample, but the stimulated Raman is a very clean signal. Of course, it's hard to catch it. You need really sensitive detection methods, but the signal is much higher than the fluorescence that comes from the sample.
Okay, thank you. The next question, biological samples are highly heterogeneous, and this means that the optical path length and the GVM will be spatially in a complex and unpredictable manner. How will your field sampling be affected by spatial dependent dispersion?
So that's a very good question. So for the microscope that we are developing, we are not thinking about, for example, putting a zebrafish, because it's obviously a very ambitious goal. So we are really thinking about very thin samples. But what we are thinking in this direction actually is to do OCT with the same technique for thick samples. So this is also a project which hasn't taken off yet, but it's in our agenda, because one can, of course, the group velocity dispersion is going to be, I mean, the pulses are going to be chirped inside the sample,
Mhm.
But the cool thing is that we can see the back reflections from the sample in our time detection technique with a very sensitive manner. And for OCT, you just need to pick these back reflections, and it doesn't matter if they are chirped or not. Right? But for the microscope, we aim just for very thin samples.
Understood. Thank you. The next question is wondering if you could go into greater detail about how how you were able to enhance your SNR or will be able to enhance your SNR. How are you able to enhance your signal relative to the background for these types of very sensitive measurements?
So you mean by the this field measurement technique that we have, or is that the question?
I believe so, yes.
Okay, so I can go to the slide if I find it. I think that's where I talk about, right? So the whole story is that when you
Sorry,
are,
could you share your screen again if you're wanting to show it on the screen?
I think it is shared, or
Not in my view.
No, not right now.
okay. If I find my Zoom. So I think one participant is sharing the screen because I cannot share my screen at the moment, or I get the warning that I cannot share the screen.
That seems to have just been cut.
Okay,
Can
so
you
I'll
try
again.
Please.
Which is not working, interesting. I'm happy that it worked a bit ago. So I can also, I don't need the screen. Actually, I can just talk like this.
Whatever works best.
Yeah. So for the when one look at the pulses with the spectrometer, the signal is sitting on top of a background signal. And the background signal is in principle the excitation pulse. So at your detection, at the spectrometer, you always have the excitation spectrum and this small absorption dip, that you have in the spectrum. But with the time domain, with the technique, with this field detection technique, in principle, the molecular response is gated from the excitation pulse temporally. And if one can manage to just look at this gated signal, then you have a higher chance for the signal to noise ratio. On top of that, there is one more reason that I didn't mention during the talk, that we aim for the time domain detection. And that's the fact that we would really aim to go to excitation to excite the samples at 1 micron, because I showed you that how such an interesting region is 1 micron. And then if you look at the spectrometers, the silicon stops at 1 micron, right? And the spectrometers, they don't have good resolution, or and you have to use 2 spectrometers to just cover the bandwidth. But with the time domain technique, you just up convert it to higher frequencies, and then you have a chance to look at the whole spectrum with one technique. So this is another reason that we are opting for this kind of measurement, time domain measurements.
I'll just ask one question of my own then. Oh no, sorry, there is another question. If I understood correctly, you are measuring the sum frequency signal to characterize the free induction decay. How much does the phase matching affect the measurement precision? Is the fieldscopy technique sensitive to the CEP?
Oh, it is very sensitive. That's the challenge of generating these pulses. So that's why we spend quite some time to generate the pulses. So the excitation pulse has to be CEP stable, because you are looking at the relative, you are just having a probe pulse which goes point by point to the samples, the pulse that you would like to measure. And if it's not CEP stable, then it's going to jitter and your signal is going to be much, much lower. So just the excitation pulse has to be CEP stable, but not the probe pulse. And then there was another question in the beginning that you read.
Oh, they're asking for, if I'm reading this correctly, they're asking for confirmation that you are measuring the sum frequency signal to characterize for induction decay, and so how does phase matching affect the measurement?
Yeah. So it's absolutely a valid question. So that detection accuracy depends on how much of the signal how much of the frequencies that you have in your sample plus you can convert and transfer this information to your sum frequency. So we are using very thin crystal at the moment, like 10 micron. So we can phase match the entire bandwidth of the excitation pulses that we have. But then that also brings us to the limitation of this technique. So in principle, you cannot go, well, maybe you can go to the UV if you use, I don't know, another type of nonlinear interaction. But with the sum frequency at the moment and the BBO that we are using, you have to stay very thin to phase match the entire spectrum.
Understood. Thank you very much. That concludes. Oh, sorry. There's one more question. Hopefully, you'll indulge me with one more question.
Sure.
Because you are exciting molecular vibrations, there should be even difference frequency generation in addition to sum frequency. Is there is it more intense than sum frequency signal?
You have the difference frequency also generated at the same time. That's true. But for the spectral, you can also do the same thing at the longer wavelengths at the difference frequency generation. But for our case, we have a better spectral overlap for the sum frequency with the probe pulses. Okay. That's why we opted for the sum frequency.
Gotcha. Okay. But can you speak to whether there's a different intensity of one produced versus the other? Or like, is some frequency is obviously more convenient for your applications, but is it also more intense or less intense than the difference frequency?
So then it depends on the crystal that you are using. So if you are using a crystal which has a high D effective for that spectral region, then of course you get a higher signal. So it depends. You can engineer it. That's what I mean. You can engineer it and get a very good signal at the DFG also.
Wonderful. Okay. Thank you very much. This concludes the questions portion. If there are additional questions, as Professor Fattahi mentioned, she's very open to having discussions further. But for the purposes of this meeting, I will now pass the floor over to Bob once more. Thank you once again.
Okay, so well, I have very little to say except meeting over, but I do want to emphasize that I thank Fattahi very much for her willingness to come and talk with us. Don't forget, please, that tomorrow we have a poster session at the end of the talks. Today, there is not a poster session at the end of the talks. So I guess that's about it. Have a great time tonight, and we will see you tomorrow.